Hi, this is an introduction to the sets and operations topic under discrete mathematics. So, what are sets? By definition, a set is an unordered collection of distinct objects, which we call elements or members of the set. A set contains its elements, so we use this symbol to denote that whatever is written before it is an element of the set written after it. So, F is an element of the set A. Using this symbol denotes that F is not part of the set A. The convention for writing sets is usually in uppercase and lowercase for elements. To write a set using the roster method is by listing elements and enclosing them with the use of curly braces. A set can either be finite, such as this set of numbers from 1 to 5, or infinite by making use of ellipses, such as the set of all positive even integers. Another method is by using the set builder notation by stating the property or properties elements must have to be members of this set. This method is usually used to simplify sets with plenty of elements. We read this as x such that x has a property P or any condition C. Or we can equate these two sets and say this is the set of positive integers such that x is less than 6. Or the set 2 times n such that n is a positive integer. Repeated elements are listed once because we only need to know if an element even appears in a set or not, and there is no order in a set. Take these two sets for example. The set of A, B, C, D, E is equivalent to the set B, A, C, E, D, A, D, D, E. No matter how many times A, D, and E or any other element in a set are repeated or rearranged, the two sets are still considered equal. Some of the common sets frequently used in discrete mathematics include the set of all natural numbers. In some books, 0 is not considered a natural number. The set of all integers, the set of all positive integers, the set of all rational numbers, which are any numbers you can write as a fraction, the set of all real numbers, the set of all positive real numbers, and the set of all complex numbers. For intervals, the interval AB with brackets is a closed interval where x such that x includes a and b. The interval AB with parentheses is an open interval where x such that x does not include a and b. These two types can be used for either side individually, so we could either use it on the left side only or on the right side only. A set can have members that are sets on their own. So this set contains the sets of natural numbers, all integers, a set that contains a and b, and even just a regular element like 6. An empty set or a null set can be denoted by this symbol, which can also be written as an empty set that has curly braces with no elements in between. Any set with only one element can be called a singleton set. Hence, this set is not the same as the singleton set, this, where the null set is considered as one element in the singleton set. If I have 3 pencil cases, one containing no pencils, the second containing 1 pencil, and the last containing 2 pencils, and place them in my bag, the bag represents the set and each pencil case can be considered an element. So, in theory, my first element is the null set, which is the empty pencil case, and the other two are pencil cases with pencils in them. The cardinality or the size of a finite set F can be denoted by the absolute value of F. Let's go back to previously mentioned sets and try to determine their cardinalities. So for the first set, A, B, C, D, and E, there are 5 elements, so the cardinality of that set is 5. For the second set, we've already established that it is equal or it is equivalent to the first set. Therefore, the size would be 5 since repeated values or repeated elements are only written once. For the third set, we're getting the cardinality of an empty set or a null set. So that means it has no elements, so that means the size is 0. For the fourth set, we're getting the cardinality of a set that contains a null set. Since we're Since that set contains a null set, it means it has one element, so it is a singleton set. For the last set, it has four elements, even though its elements are sets of their own. A Venn diagram can be used to visually represent a set. In Venn diagrams, the universal set U contains all objects or elements and is represented by a rectangle. Sets which are represented by circles are inside the universal set. In this Venn diagram, A is the set of numbers from 0 to 5, and B is the set of numbers from -5 to 0. We can see here that 0 is a common element between the two sets. Hence, it is in the intersection area because it intersects both set A and set B. So, in summary, we can use Venn diagrams to show relationships between sets. A subset is where elements of a set are also the elements of another set. We use this symbol to denote that a set is a subset of another set. The line under shows that the subset must have less or equal amounts of elements than its superset. In this example, by using a Venn diagram, A is a subset of B. If there's even just one element that is in set A but not in set B, then A is no longer a subset of set B. Thus, we use this symbol. Likewise, set B is the superset of set A. To denote a superset, we use this symbol. The following sets are subsets of set B. So since set B contains A, B, then the sets AB is a subset of B, and the set A is a subset of B, the set B is a subset of B, and an empty set or a null set is a subset of B, where a general rule is a null set is a subset of all sets. A power set is the set of all subsets of a set S. For example, for set S, which contains 1, 2, and 3, the power set of this set is the set that contains a null set 1, 2, 3, 1, 2, 2, 3, 1, 3, and 1, 2, 3, which is itself. The empty set and the set itself are members of this set of subsets. A null set has only one subset, itself. The set of an empty set has two subsets, a null set and itself. If a set has n elements, then its power set has 2 raised to the n elements. Since sets are unordered, a different structure is needed to represent ordered collections. We can call this ordered n tuples. Two ordered n tuples are equal if and only if a sub I is equal to b sub I, for I must be a positive integer. Ordered 2 tuples are called ordered pairs. The ordered pairs A, B, and C, D are equal if and only if A equals C and B equals D. A, B, and B, A are not equal unless A equals B. Let A and B be sets. The Cartesian product of A and B, or A times B, is the set of all ordered pairs AB, where lowercase a is an element of the set A and lowercase b is an element of set B. Let's have a few examples. Set A contains the elements D, O, G, and set B contains 0 and 1. Determine the Cartesian product of A and B, which is A times B, and its cardinality. Since A times B is not equal to B times A, we have to write the ordered pairs properly. This is D0, D1, O0, O1, G0, and G1. Therefore, A times B equals the set of all these ordered pairs. And since the cardinality of A is 3 and the cardinality of B is 2, that means the cardinality of A times B equals the cardinality of A times B, or 3 times 2, which is 6. The Cartesian product of B times A would just be the same, except each ordered pair must be interchanged. It is possible to have a Cartesian product of a set and itself. We denote this by attaching power exponents to the name of the set, s raised to n. For set A, 0, 1, the Cartesian product of this is a raised to 2 is a raised to 2 is equals to 0, 0, 0, 1, 1, 0, and 1, 1. A subset R of the Cartesian product A times B is called a relation from set A to set B. The elements of R are the ordered pairs. So we could say R of the set of all the ordered pairs is a relation from the set DOG to the set 0, 1. Under set operations, two or more sets can be combined in many different ways. The union of the sets A and B is denoted by A union B, which is the set that contains those elements that are either in A, in B, or in both. A union B is in the shaded region. The intersection of two sets is denoted by A intersection B, which contains the elements in both A and B. A intersection B is the shaded region. Two sets are called disjoint if their intersection is the empty set. The difference of A and B is also called the complement of B with respect to A. It can also be denoted by the backward slash. So A backward slash B. The area that's shaded is the region. Since U is the universal set, the complement of set A is denoted by A, which is the complement of A with respect to U. Therefore, the complement of set A is U minus A. The shaded region is the complement of A. To identify the universal set U, simply take the complement of A with respect to set U. Under set identities, there are 10 set identities that are very important, especially when dealing with unions, intersections, and complements of sets. These are also called laws. The first law is identity, followed by domination, idempotent, complementation, commutative, associative, distributive, De Morgan's, absorption, and complement laws. We can prove these identities by using three different methods: the subset method, membership table, and by applying existing identities. For the subset method, we show that each side of the identity is a subset of the other side. For the membership table, for each possible combination of the atomic sets, show that an element in exactly these atomic sets must either belong to both sides or belong to neither side. By applying existing identities, start with one side, transform it into the other side using a sequence of steps by applying an established identity. This is to show that you can have several approaches to a problem and that there's not always only one solution. Now, let's try one final example. Prove that the complement of the intersection of A and B is equal to the complement of A in union with the complement of B. The first step is to set this by the definition of complement. Second, by the definition of does not belong symbol. Then, by intersection. Then, by De Morgan's law. Then, by definition of does not belong symbol again. Then, complement, union, and finally by meaning of set builder notation to simplify this and equate this.